Guys, welcome to MathSpellBook. I'm your host Peter, and we're going to engage back into some real analysis today. Hopefully you guys are having a really great week so far. It is Wednesday, so Wednesday is the middle of the week, and it's the first day of October, so if you guys are living in the States, you know what that means. Halloween is just going to be a few days away, so if you guys actually want to put in the chat on what you plan to dress up for as Halloween, or if you don't plan to celebrate or just watch scary movies in your home, that's also a thing too. I try not to watch too many horror films because even though I would probably be okay during the viewing, I know that once I go to bed, I will probably have my eyes opening on and off, just basically trying to get over the haunting stuff that's going on in my imagination from the horror flicks. So that's something to keep in mind. So let's see. So we were working on this question last time. Assume that A is a subset of B and both are bounded above. Prove that the supremum of A is less than or equal to the supremum of B. Now, I did try to work on this a little bit last night after stream. I did take a peek at the solution thanks to ChatGPT. So I'm just trying my best to remember exactly how to set this up. So, okay. So let's assume A is a subset of B. And A, B is an element of R, which is let's assume set A is a subset of set B. Hey Hans, what's the best part of your day so far, my friend? Set B. Well, actually, maybe first we should say what they are. So, first off, let set A B be an element of, well, actually, would they be an element or would they be a subset? I'm pretty sure you can think of something. Well, then again, yeah, I think maybe an element, because sets can also be elements of within sets. So it's an element of R. Well, actually, it's supposed to be an ordered field, so. No, actually, let's set A and B. I don't like the way that B looks. And B is an element of R. And A is a subset of B. Listening to music? Yeah, there you go. Actually, okay, assume A is a subset of B and both are bounded above. So, according to our definition of bounded above, A is bounded above if there exists B in S such that X less than or equal to B. Not very often, actually. I mostly like watching a lot of stuff. All the music I have in my computer is all Japanese pop. And usually all the music I have is from like anime and stuff. I haven't like downloaded any new music like in a long time, actually. Let's see, such X. Let's see, the least upper bound of A. There exists some. Okay, so it's bounded above. Okay. Since A is bounded above, there exists A in B such that X is less than or equal to A for all X in A. Thus, A is, well, I don't think we need to write all that because that's basically bounded above. There exists an upper bound we'll call it A naught. Let's see. Such that regular A is any other upper bound of A, then A naught is less than or equal to A. Thus, A naught is equal to the supremum of A. Okay? Now, since A is a subset of B, the supremum of A is also an element of B. Set B to be. Of course, this is pretty wordy from what I'm writing, but I feel like that's the best way I can like layer out the logic. Okay. So we already established this. Is the supremum of B. Okay, now we have to connect it all. I'll be right back, guys. I just realized I forgot to fill in my water. see. Sorry to keep you guys waiting. Okay, so getting back to where we were. Now I gotta figure out how to write the last part that allows us to complete the whole thing. And the thing of it is that I have to ensure that basically we know that the supremum of due to the fact that both the supremum of A and the supremum of B are elements of B. GPT and tell, because I feel like I'm going to have holes in it, but I feel that this might be a better approach to actually better understand the holes in the logic I'm making. he says. I feel like we're gonna have to fix some things in this proof. I feel like I'm having some holes in the final part here. How they write their proof, because I've seen it last night, but because like, yeah, like they wrote it so short, and I'm like, what is it that I am forgetting in this distinction here? That's the one thing I forgot to understand. It's like, I knew that this was going to be less than this. It's just that I didn't know how to explain it in the correct way. Alright. I mean, at least I did some of the work to basically like show that I made an effort to try to remember this. The thing of it is that like with proofwriting, it's kind of hard because it's like, what am I lacking? What am I not taking into account? I think that's like the struggle of actually learning this stuff. Plus, like whenever you look at the proof that like, you know, the answer, you feel as if like, wow, I didn't know anything. But of course, like the mindset is to basically say like, hey, like looking at the solution doesn't mean that like you wasted all that thinking time, or like basically like you didn't do the question, like you didn't make an attempt to solve the question or whatever. I think that's the one thing I have to like turn off in my brain, because whenever I see the solution, it feels as if like, wow, I totally didn't put enough effort into it as much as I should have. But like, you know, that's the part of the brain I have to turn off, because it's like doing proofs is like it's not like you basically have to look at every single step. It's more like you're always going to feel like you're like not going to be able to put in a lot of I guess like there's always going to be things that have gaps, and like you're not going to write every single thing, or you might write too much, or you might put too much emphasis on one definition when it shouldn't be. And I think that's the thing that's really tough about writing proofs, is that you don't know which definition to aim for, and that's usually like the tough part. So yeah, I try not to be too disappointed about the stuff that I kind of like have to look up, because it's like I just don't know it. And you know, sometimes like when you guys study, you got to give yourself that type of humility to basically say, hey, I don't know it, and you know, because I don't know it, that doesn't mean I failed. It just means that I have gaps. Okay, so I think we're given the same type of question. So let A be a subset of R, and assume that the supremum of A is less than the supremum of B. So they have nothing in relation. So A and B, we don't know anything about any relationship between them. So I'm guessing they're just random subsets. But for some reason, so for A, show that there exists an element B that is the upper bound for A. so, but they're not subsets of each other, so that makes it a little bit difficult. Okay, so let's just write this. Let A be a subset of the real numbers and assume that okay, so I think we'll just write this all out because there's nothing relating A and B here, so we just have to find a way to actually show that somehow there's a B in B that is the upper bound of A. So, and what does B say? Give an example to show that this is not necessarily the case if we instead only assume that the supremum of A is less than or equal to the supremum of B. You do not need to prove your answer. So I'm guessing once we do this, we probably have to like kind of see why this case occurs. So let's see what so in this one, they basically said that the supremum of B is the upper bound of B, and because then every element of A is also in B, so the supremum of B is also the upper bound of A. And by definition, the supremum of A is the least upper bound of A, since the supremum of B is the upper bound of A. That shows, oh, okay. So I think that's the reason why the definition, like right here, it says that the supremum, that there is an upper bound that is greater than or equal to the supremum here. So I'm guessing it always says that the supremum is going to be like, if you think of it in an interval, it's going to be the last number of the interval. So, I mean, that's the way I can visualize it. So we have to think about the definition of a supremum, which is right here. So supremum of A is in A, and the supremum of B is an element of B. And which are both in R. So I think we probably might need this this definition here. So let S be an ordered set. Then has the least upper bound property given any non-empty set A, where A is bounded above. A has a least upper bound. In other words, the supremum of A is for every such A. Maybe we can use this. Because this definition is for one set, so if we have two sets, then so basically because the one thing is that we have to show that A is less than B, like at least in subset Y, so we can actually have the supremums like because I know it's not just an ordering thing. Because I feel like it's in the definition here, so it's like, so because we have supremums here and they're part of R will have the least upper bound property. And because these two are bounded above, because they have supremums here, so maybe which both A and B are bounded above this since A, B are subsets of R, then R has the least upper bound property. A has the least upper bound, in other words, the supremum for every such A. But now the hard part is like, how do we actually show that A is the upper bound of A is, or the least upper bound of A is less than the least upper bound of B, or the supremums of them? Like, how do we do that? That's the one thing I'm trying to think about. I'm trying not to dwell too long on each problem, so it's like, because I'm trying to measure like each time I do a problem, I'm trying to make sure that it's like takes at least 20 minutes. So assume that we know that the supremum of A in A and in the supremum of B is in B, which both A and B are bounded above. Since A and B are subsets of R, then R has the least upper bound property. Thus, the supremum of A in R for every such A, and for the supremum of B for like one subset of like an ordered set here. Now the one thing is that what does that mean if there's two sets? That's the one thing, because we know that R is complete. The one thing is that because like for supremum, the one thing I'm having a hard time with is like, how do we actually show that this relationship exists? So let's see what they did. I'm going to take a look at this one again, because I feel like this could help us in some way. So we can ignore this part. Let's see, by definition, least upper bound of A, and then B is an upper bound of A. But this is when they're subsets of each other. Now, if they're not subsets of each other, do we have to do this by a case-by-case basis, or what? questions is that it involves like 2 sets. And I think that's the thing that makes them challenging. Because like these definitions fit well when it's like 1 set. I mean, like it doesn't make it obvious to do it with 2 sets. Like within like the ordered field. So when it's like 2 sets, you feel as if like you have to ask so many questions. Like, since these two are not subsets of each other this time, I have to ask like, is there more elements in B than there is in A, or is there like is A in a specific region of the real numbers where B is, and like is B like overlapping A in some ways? Like I have to ask so many questions on how to actually like make this work, because the only thing I can think of is that the supremum of A, like let's say if A is like from 0 to 1, and then we have the supremum of B, which is from like maybe like around like 2 to 3, like on the number line. Like that's the only way I can think of like that involves like basically them being like having this relationship, like this relationship here, but we're not really given those type of details. So maybe we should check what A asks. Like A asks, show there exists an element B in B that is the upper bound of A for A. Okay, so maybe like let's ask what an upper bound is. Oh, here we go. So A is bounded above. There exists such that X is less than or equal to B, and for all X, in this case, B is the upper bound. So maybe we should use that. So let's see. So there has to be an upper bound. Let's see. A set A is bounded above if there exists a B in such that. So I feel like this can help us like answer this question. So show there exists an element B that is the upper bound for A. So of A is less than there exists
like I should erase this part because it's just like too much stuff here. So, because I don't feel like that's the right way to view this. Definition of supremum for any epsilon, there exists some element B within. Okay, so maybe we have to think of this one. I actually wasn't thinking about this one. So it's the upper bound and given any epsilon there is some x in A for which x is greater than alpha minus epsilon. So let's see what the hints are. You know the supreme of A. Let's call the gap delta, and notice that delta is greater than 0. By definition of supremum, for any epsilon greater than 0, there exists some let's just address the gap between the two instead. So if that is the case, let delta be the difference is greater than 0. Oh, thank you for the follow. Refees? I don't know if I'm pronouncing that right. I probably pronounced that wrong, but what's the best part of your day so far? And thank you for the follow. Much appreciated. Please tell me how to pronounce your name correctly. I want to make sure that I address you in the way you want to be addressed. Because I'm reading it as I think it's Refees, I think, or Feast, because it has a ST at the end. If I'm mispronouncing it, I do apologize. So let's see. By definition of supremum, okay. So I think it's this definition. Given any epsilon is not an upper bound of A, that is, there is some I think I have to look for when they have the delta, because right here, and okay, let's just read what it says here. I will note that the epsilon terms will be used a lot. Always think about them as being some small positive number. Also, in part, because I need to find the relationship between delta and epsilon. The Archimedean principle. alpha minus epsilon is not an upper bound of A. That is, there's some x in A for which x is less than alpha minus epsilon. Already spent like more than 20 minutes on this, so I guess I'm gonna have to wave the flag of surrender. All right. Let's see how this is supposed to go. Okay, let's see. Since A's define the difference. Okay, so we didn't even need that part with by definition of supremum, for every there exists some B in B. Oh, okay. I'll choose epsilon to be as delta minus delta. Is greater than SB is. Oh, okay. That's a interesting way to write it. And it makes sense. I remember Sasha telling me that, like, with epsilon, it's like, you know, you'd be used to writing a half a lot with that. I'll give an example to show that this is not the case necessarily. So example, but the only element B is 1, while 1 is the upper bound for A. It is not strictly greater than the supremum of A. if we modify A slightly says, yet no element of B appears to be an upper bound. That's the statement. Assuming that it fails when. I gotta read that over. So, okay, we're given this interval, and then we're given this set. So the supremum is equal to 1, okay. But the only element of B is 1, while 1 is the upper bound for A. It is not strictly greater than the supremum of A if we modify A slightly, saying yet no element of B is the upper bound of A. Thus the statement fails. Okay. So maybe I have to keep this in mind the next time I encounter this question. Knowing me, I'll probably end up like going back to this question over and over again until I actually get it. But then I would probably just turn off my brain and just like let myself kind of like let myself forget it, and then I would try to come back to it. Because the last one we have here, just basically trying to think about like the question, like what did I learn today with these proofs? And I think what I've learned is basically just like the setup, in addition to like how I guess they're defined within like the parameters of the proof. Because I know like a lot of people when they do proofs, like a lot of people that know how to do them, they say focus on the definitions. But at the same time, it's like when you're actually writing them down into a proof, that's when you have to think about like, or at least for me, that's when I have to think about like how does the definition fit in the proof. And sometimes when I have the definition in front of me, I sometimes wrote too much because the definition itself is like very elaborate, but it's probably not looking for that. It's probably looking for just one part of it. All right. I would be lying in saying that I'm kind of disappointed, but in myself for not being able to figure that out. But at the same time, it's like that's usually how it is with proof-based math or any type of like science. You feel like you know it, but at the same time, like you realize that how little you know, or like I think you just get used to the fact that there's some places where you're inadequate when it comes to like trying to figure stuff out. Okay, so Sasha told me that this one was going to be a pretty tough one, so I feel as if oh, I think there's a little footnote here for 31. Closed interval is defined that you should expect. Okay, so maybe we should also take that hint as well, because it's meant to help us. Okay. So, for each n in n, assume we are given a closed interval in is equal to an bn. Also assume that each in plus 1 contains inside in. This gives a sequence of have increasingly smaller intervals. Okay. Prove that the intersection I to infinity is not the empty set. That is proof that there is some real number x such that x is an element of in for every n in n. Okay. So basically x is in in and the intersection, because I think in the book they say that this question prepares you for topology, so we just have to figure out exactly how we can start this. Some assumptions here. Okay, the closed interval is defined. So we should probably write that down. Guess we'll write it over here. I'm trying to make sure that I don't get it cut off from the chat on the side. Such that likewise an open interval and a half open interval to infinity are again exactly as you expect. Okay. So okay. So we have to prove Okay, given the sequence, proof that. So basically, I1 is a subset, so all the elements in I1. So basically all of them contain each other at that point. So let IN equal and IN basically this is the reverse, because I thought it was subset, but this is basically saying that I contains I2 and I contains, so basically they all contain each other but from like the opposite direction. So I1 contains like every single thing here. Now basically contains all the sets in here. Unless they wrote that backwards. I mean, I don't think that's what happened, but... Because it says that, assume that each I plus n is contained inside... Oh, okay. So basically it's... So the previous one contains all of it, so... So it has to contain all of these. So... I mean... I mean, each one of them would have to contain, like, each one of them would have to contain, like, an X in between. A real number X that is contained within IN. Actually, I can erase this part. And then write this. structured. I feel like that might be the solution. ChatGPT critique it. I probably missed a lot of details with it, so I'm prepared to face the music with that. So we're still not done with it, so okay. listed. So that is increasing. Now this part I don't get, like why is it decreasing and this one's increasing? I mean, why does this increase and why does this decrease? That's the one thing I'm not getting here. Inside IN in particular, the left endpoint satisfies because I am smaller than one thing I'm not getting is like, how is it? Where does that imply that? Yeah, because it doesn't really show where B and A are different in values. That's the one thing I'm not understanding here. Directly from nesting condition. Let me spell it out carefully. So the smaller the interval cannot stick out to the left or to the right. still don't quite get it. Might have to ask Sascha about that one. It says nesting condition, and I'm like, I don't quite understand that. See, since so I'm guessing like the way they phrased it is that they just want this to, like, each one of these is basically within this interval here. Like every little bit goes in here, kind of like its own number line going in a number line and a number line, like an endless kind of thing. Well, I mean, we did do the problems. The problem is that I had to look up solutions for like a majority of them, so I still have a long ways to go before I can actually say that I totally understand these proofs, but at least we got some of them. Like, I mean, we did do this one, the induction proof one, and this one I think we managed to do, which I'm surprised about, but we managed to get through this one. Just move this to the side. This one is just an old friend, so I knew we got that one right. This one we just basically had to think of the numbers. This one I think we used a lot of hints, but I think we just got it from like contradicting things. Because I think, what was it? The last three we still have a lot to like. I probably might have to ask Sascha about these. Hey, Enstunky. I'll give you a shout out, Enstunky. If you guys are not familiar with Enstunky on Twitch, he's another awesome math slash I guess you can say like basically he also does programming as well, so like he does a lot of math too, so be sure to check out his stuff as well. Let's see, Math Twitch is popping today, but I wanted to pop in while you were live. Thanks, man, appreciate it. Doing yeah, so today was not really it was a very trying day because I had to rely on ChatGPT for the 3 problems I was doing. This one I saw last night, but unfortunately I wasn't able to remember the structure. I thought I would be able to reproduce the proof, but I just didn't remember. This one I had a hard time with. Like the solution I saw, it kind of made sense to me, but at the same time I was like, wait, I'm still lost. So basically it was that type of day. Like mostly taking L's for learning. Taking L's for learning mainly. This one I have to actually like this one I think I have to like basically like have to go back to, because I don't really understand exactly why is it like that, because I looked at the solution and the thing of it is that I don't understand why is it that A in this case in this interval is increasing while B is decreasing, because like the question itself, it doesn't really like, I think like it's not obvious to me because like maybe I don't know a definition or something. But I don't, because it says like I plus n, in plus 1 contains, is contained inside in, and it basically that is supposed to indicate to you that the left side is increasing and the
right side is decreasing, and I'm like, wait, what? I don't see how that. I don't see how that those two relations are actually equivalent. So like that was the thing that I was kind of like a little bit confused, and I think I'm still confused about that, because it says so that an is an increasing sequence and bn is an increase. And I didn't know these were sequences. I thought they were points, because I thought it was just a closed interval. But then again, like maybe like that's the way they wanted to set it up for that. It's bounded by points, and then they say you have to add completeness to it. So I didn't know we had to do the limit, and actually in the book we didn't really learn about the limit yet. So I guess like this one was sort of like one you actually had to like really go deep into the weeds. So the limit for this is the supremum. Yeah, and it doesn't really indicate that an is supposed to be greater than, is supposed to be less than or equal to bn. Like, there's a lot of assumptions here that I'm like, wait, where'd they come up with that, and where'd they come up with this? I mean, they're probably not assumptions, they're probably like logical conclusions. It's just that I'm not understanding where these conclusions are drawn from. And I think that's the thing that kind of makes me a little bit iffy with this proof. But this proof is supposed to be a good way to introduce a little bit of what topology has to offer. Because according to the book, this question is supposed to be kind of like I guess a little bit of taste of topology in some way. I don't know how, but like I guess that's what the intention was for this proof. So maybe I'll have to ask Sasha more about this one. But I mean, it feels like, for me, I still don't fully understand supremum, like supremum and boundedness yet. But at least we got these problems done. So I think probably over the week I'll have to like analyze the problems that I didn't do well on and try to understand it better. The supremum is really weird concept to use. Yeah. Oh, okay. So I guess like that's probably part of the journey. I try not to complain whenever I don't get a problem right or when I don't understand a problem, because like complaining about it doesn't work, doesn't help. In addition, I try my best to actually like remain not so negative whenever I have to look at an answer, because I know it's meant to like to teach me, but at the same time it just feels like, you know, like you can't ignore the feeling of defeat when you realize that, wow, this is the limit of my knowledge. But then again, that's also a good thing, because it's like you're actually interacting with the thing that you really have a gap on, and I do have a lot of gaps when it comes to mathematical proofs. Conceptually, it's just like bigger, but not too big, but translating that into actual use takes some brain triggering. Yeah. I'm glad that you're actually giving the words of support there, and Stunky. I probably needed to read those. Because, I mean, like, I know a lot of people that make content about math, they basically explain the math and they try to teach people, like, the math they know. But for me, I'm just a person that is probably just doing the regular trudging about, where it's like I don't know anything about math, but like every one of my streams is like me getting it wrong or me looking up the answers, or like I probably get it wrong more often than I get answers right. So, you know. But of course, like if the channel were just about me succeeding and just doing math problems, then like, you know, it wouldn't be a journey either way. Because the thing of it is that, like, what do most people that like math look for in like math content? They probably look for more knowledge involving math that they haven't touched yet. I mean, I know I do. I know I'm that type of person. But it's always great whenever you guys stop by, even though when I get things wrong. I always appreciate it. But I guess I'm going to have to ruminate on these problems for now. But at least we got chapter 1, like the stuff that Sasha assigned us, done. I mean, granted that I didn't really do a majority. I mean, I did try the problems, but I didn't get them right, so... Or I didn't write the proofs, like, cleanly as I should. But then again, that's usually part of the experience. So I guess throughout the week, we're gonna have a lot of work on our hands. And then, like, I think with the real analysis book, we're probably gonna go into chapter 3. Because chapter 2 is cardinality, and Sasha says we don't really need that right now. So, let's see, what is page 100? This is sequences. Okay, so this is chapter 3. Yeah, because like the last question, we actually have to use limits, and I didn't learn limits yet. But I guess that's why the author put it there, to basically say, oh, give this a try. You don't have the material to do it, but maybe you can give it a try and see how it goes. Yeah. So maybe that problem was meant for you to like kind of like read ahead or something like that, or see what you know. Because actually, what did the author wrote about the last question we did? Let's see. Because I know he wrote something in, because it's notable. Okay, here we go. Exercise. A special case of important typological property we will study in chapter 5. You are asked to prove the generalization of it in exercise 5.4. Although best way to prove exercise 1.22 at this point, utilize only things we discussed in this chapter. And I tried to utilize them, but I did not get it right. But then again, I also got my answers from ChatGPT, and the author, I don't know if he posts like the answers on his website. I think he does, but that will do it for another time, I think. I'll probably look it up like during the week. Let's see. I think let's try page 90. Because I just want to take a brief look here. Because we're going to be doing sequences in chapter 3. And I'm going to try to read this also during the week, so that I can get a better understanding of what is it. Because I didn't know those were sequences we were working with that problem. But I think that would probably be a good intro for that. So maybe like I can go back to that question again, and maybe with my new knowledge I'll be able to like solve it, or have a better time solving it. Like maybe like have a better idea of what I'm looking for. Okay, it's almost about that time, guys. Thank you for joining me today. If you guys are watching this on YouTube Live, you know, like leave a comment down below, as well as hit the like button, as well as like hit the subscribe button if you wish to keep in tune with my math/physics journey. Always appreciate you guys stopping by, and maybe you guys will also be able to share your knowledge with me if you see something that I'm doing wrong, or if you see that the gaps in my brain are being revealed to you guys, and you can probably help fill in the gaps for me that I'm lacking, or give me an epiphany that I'm not thinking about. And if you're watching this on Twitch, you know, drop me a follow. I always appreciate it, especially like for people that love math or physics and need a study stream to keep themselves productive during either the school year or during, you know, just their own like working journey, just like trying to catch things, like trying to be productive online and all that stuff. So there will be a link to our Discord server in
the description down below if you're watching this on YouTube. I will post it also in the Twitch live chat. So for all those that are stopping by, thank you very much. And I will also be posting my video game channel, my Uncle Talks channel. If you want to catch us playing video games, I will be playing Mahjong Soul with my friends tonight. So usually those type of streams are very fun because we do tend to get a little bit like very competitive with Mahjong Soul. So there's a lot of like laughs during those streams. So thank you for joining me today, guys. And also for my Twitch viewers, I will also post my YouTube channel there, so you can also support me on YouTube if you just want the streams to be your background noise for studying. Okay, so that will be all for today, guys. And always remember, everyone is precious. You guys are just as precious as everyone else. And I will see you next week for the next chapter of our journey. So take care, guys. Bye-bye.